There's a photograph from 2002 that nuclear engineers still pass around, and the reason it's frightening has nothing to do with radiation. It's a hole. It goes through 6.5 inches of solid steel. It's roughly the size of a football, and it's in the lid of a working nuclear reactor. Underneath it, the only thing left holding back the coolant is a layer of stainless steel about as thick as 2 stacked pennies. It was already bulging upward. It was already cracked. And nobody had been looking for it for 6 years. Start with the lid, because the whole story is about how thick it was, and because you can't see it. The reactor pressure vessel head at Davis-Besse is a domed cap of low-alloy carbon steel. It's 6.63 inches thick. It weighs 81 tons, 60 studs, each 2/3 the diameter of a soda can, bolted down onto the vessel. Inside that vessel is water at 2,155 pounds per square inch, at 605 degrees Fahrenheit. It stays liquid because the pressure won't let it boil. Now look at the inside face. Bonded to it is a thin layer of stainless steel called cladding. Design thickness, 187 thousandths of an inch, 3/16. That's 1/35 of the head's thickness. That cladding is not structural. It was never structural. Its entire job is to stop the borated coolant rusting the carbon steel underneath. The steel holds the pressure, the stainless just keeps the steel clean. 69 tubes penetrate that lid. They're called control rod drive mechanism nozzles, and the control rods run down through them into the core on a 12-inch grid. They're made of a nickel alloy called alloy 600. In 1971, when this reactor was designed, alloy 600 was the obvious choice. It was strong, it handled heat, and it didn't corrode. That last part turned out to be wrong. How do you fit a tube through a lid that's holding back 2,000 psi? The tube is pressed into a 4-inch bore through the lid. The fit is tight, 6/100ths of an inch of interference, metal against metal. Then it's welded, but only at the bottom, on the wet side, in a ring called a J-groove weld, only at the bottom, which means that above the weld, for the entire 6.5-inch thickness of the lid, that tube isn't sealed to anything. It's just pressed in. There's a gap, and the gap runs all the way to the top. So long as the weld holds, that gap is dry, and nothing happens. Alloy 600 cracks. Not because it was made badly, it cracks because of what it's sitting in. The failure mode is called primary water stress corrosion cracking, and it needs 3 things at once: a susceptible material, high tensile stress, and hot water. A reactor vessel head supplies all 3, permanently, and the welding itself leaves the metal locked in tension before the plant has ever run a day. So the clock starts the first time the plant heats up. The alloy cracks slowly, over decades, along the grain boundaries. By 2001, the industry knew this. Cracked nozzles had been found at plants across the world, and they all behaved the same way. The cracks stayed low, near the weld. Across every documented case, they extended no more than about 6/10ths of an inch above the top of the weld. Nozzle 3 at Davis-Besse cracked 4.08 inches, all the way through the wall, and it ran 1.3 inches above the top of the weld, more than twice as far as any nozzle anywhere had ever gone, which meant, for the first time, the crack opened above the seal, into the gap. So now you have 600-degree water at 2,000 psi, with a path. It leaks out of the crack, into the gap around the nozzle, and it climbs 6.5 inches, up through the lid and out onto the top surface, and the instant it reaches open air, it flashes to steam. That flash is the whole disaster. Boiling water absorbs an enormous amount of heat, and it strips that heat straight out of the surrounding metal. The steel around the leak drops from 605 degrees toward 200. So what does that leave on top of the lid? Every inspection procedure in the country was built on one answer. The water boils off, it leaves dry boric acid crystals, and dry crystals barely touch steel. Boron on the head was housekeeping, not an emergency. That model is the entire reason this happened. The metal around that leak is cold. It stays wet. After Davis-Besse, the NRC wrote this into a formal bulletin. The findings at Davis-Besse bring into question the reliability of this model. Concentrated, hot, and wet, boric acid eats carbon steel. It runs downhill across the dome under gravity, so the attack spreads sideways as it goes. But it doesn't touch stainless, so it ate down through the lid, reached the cladding, and stopped. which leaves the stainless holding the reactor. That thin layer whose only job was to keep the steel clean is now the pressure boundary, and nobody knows it's there yet because nobody is looking. 6 years. What was the plant seeing? In 1996, and again in 1998, and again in 2000, boric acid deposits were found on that reactor head. Not white, rust-colored, red and brown. Radiation monitor filters kept clogging. Containment air coolers kept fouling. Both are exactly what you'd expect from boric acid aerosol in the air. Here's the plant's own log entry from the 12th of April, 2000. Decon people broke to the inside of the RX head with crowbars. Do not recommend use of water or steam, better to justify leaving boron on head. Washing it off was more trouble than it was worth, so they left it. And in May of 2001, a Davis-Besse engineer gave an internal presentation about boric acid corrosion. On one slide he wrote, "Did not recognize red-brown boric acid deposits, each major wastage." He closed the presentation with a joke, "May your boric acid always be white." 10 months later they found the hole. There's one more thing, and it's the closest this story comes to an excuse. The head is buried. Above it sits insulation, then the drive mechanisms, then a steel service structure, 18 feet tall and 10 feet across. To look at the lid, you feed a camera on a pole through one of 18 small openings, each about 5 inches by 7. Nozzles 1 through 4 sit dead center. First Energy later admitted those 4 could never be visually verified at all. Nozzle 3 is one of them. That's the excuse. It runs out in August 2001. The NRC issues Bulletin 2001-01 and orders operators of the most susceptible plants to inspect their alloy 600 nozzles by the 31st of December. Davis-Besse was on that list. First Energy asked to wait. "Let us run until the refueling outage in spring," they said. Shutting down early is expensive. The NRC drafted a shutdown order. It never issued it. The agency's own Inspector General examined that decision afterward and concluded that it was driven in large part by a desire to lessen the financial impact on FENOC that would result from an early shutdown. Asked about it, the head of the NRC's Reactor Regulation Office said this: "If we have flexibility and we can reduce the regulatory burden by making a different decision, and we still maintain safety, then that's fine. We should take that business case into consideration. And that's no different than any decision we make." Nobody in that sentence thinks they're doing anything unusual. They let it run to spring. The deadline was the 31st of December. They found the hole on the 2nd of March. 61 days. March 2nd, 2002. Crews are finally inspecting the nozzles, and they find the cracks. They start repair work, and during the repair, someone notices that the metal beside nozzle 3 isn't there. The cavity is roughly triangular. It starts at nozzle 3 and widens as it runs downhill toward nozzle 11. 5 to 7 inches long, 4 to 5 inches across, and it goes through the full 6.5 inches. It's wider at the top than the bottom, a funnel, with an undercut shelf at the low end. Somewhere between 40 and 60 cubic inches of the reactor lid are simply gone. And at the bottom of it, the stainless cladding. Measured remaining thickness, 202 thousandths of an inch at the thinnest point. It had been pushed upward into the cavity by 12 hundredths of an inch. Across roughly 2 inches of its surface ran a network of stress corrosion cracks, some of them 40% of the way through. That's 3% of the original wall, holding 2,155 pounds per square inch. The stainless was never supposed to hold anything back. By March of 2002, it was the only thing that was. The NRC's research office later put numbers on it. Median margin to burst, 1.4. Median time remaining before failure, 5 months. Not 5 months from the leak starting. 5 months from the day they found it. I'm not going to tell you this was almost a meltdown, because I don't think it was. If that cladding had let go, it would have opened a hole about 8 inches across, roughly 100 square inches. The plant's emergency injection systems were designed for a break 20 times larger than that. Most analyses say Davis-Besse would probably have survived it. Probably. The fine was $5,450,000, the largest single fine in NRC history. The Justice Department took $28 million more. 2 employees were convicted, and the plant sat dark for 2 years. And there's a footnote that tells you nothing had changed yet. In January of 2003, while Davis-Besse was still shut down and defueled, A computer worm called Slammer got into the plant network, not through the firewall. The firewall was configured correctly. It came in through a T1 line that a contractor had run behind it, which nobody in plant engineering knew existed. It took out the safety parameter display system for 4 hours and 50 minutes. Nobody had to report it. The threshold was 8 hours. The lesson of Davis-Besse isn't that America nearly lost a reactor. It's that for 6 years the evidence was sitting on top of the lid, in plain sight, rust-colored, and every single system built to catch it decided it was somebody else's problem. The steel was the only thing keeping score.